Welcome to another webinar session. Today's discussion will be on the shear wall, modeling, analysis, and design in ETABS. So agenda is very simple, that we would be discussing the modeling options available in the program and the requirements for the Pier and Spandrel labeling, which is necessary for the design, and a brief discussion on the design and other options within the design modules. And along with that, we also provide our recommendations in the modeling and design. Let us start with the modeling. We will explore this in an example. Basically, the modeling of the walls, drawing, and the tools available for that. So how quickly and easily you can create the walls. And then we will also discuss the meshing that is to be done and when. And the Pier and Spandrel labeling. So all of this we will discuss in an example. Let me switch to ETABS. And I will create a new model using the built-in settings with metric SI for Indian codes. Six meters in X direction and 4 meters in Y direction, and some 7 stories. And we will take grid-only option so that we can create all the objects by ourselves. The focus here would be on the modeling of the walls. So I'm going to use the default section properties and material properties that has come along with the initialization. Let me quickly jump to the draw, and let me start with the columns. So in this modeling, I'm going to place a C-shaped wall symmetrically placed on B and C grids, and rest of the locations there will be columns. I'm going to use the concrete column. Right. I could have done it with all stories. Let me do this once again quickly. Let us place the walls. For walls, we have the option to draw it manually, or you can pick up from wall stacks readily available. We'll go with the wall stacks. You can see various frequently used shapes of the wall stacks are available for you. For example, it is a core wall, then you can go for a single core wall, multiple core wall. Options are available, and with openings you can directly specify. For this, I'm going to use a simple C-shaped wall, and I'm going to specify the length of the web and the flange thickness, say 250. And that's all. You can see the schematic diagram along. And then if you press OK, then you'll have to place this where you want. And for placing, you can also utilize the draw snap options and enable the snap options that you want. In this case, I'm going to place this in this corner, B2 grid. And symmetrically, I want to place this on the C grid. I'm going to change the angle. I'll rotate it by 180 degrees. And you can see snaps. Utilize the snap feature and click. You can clearly see how the walls are getting created quickly. That's all. Let's finish this with beams and slabs. Quick draw beams. And we'll use 2-point click option for drawing the beams again in these locations, which are not connected to grid intersections. Let me use concrete beam. You can also draw the openings directly on the floor slab. That is also possible, but I find this is convenient for me. We draw a slab section. We'll make sure this is a membrane type, 150 mm thick. Draw walls quickly. At these locations, I need to create this opening. I'll remove this. I will draw it in a different way. So I'll use draw, floor, quick draw. You can use points. It quickly finishes. Switching back to one story. Remove the unwanted objects at the base level. Previous selection and assign them with restraints fixed base. We save this. All right. So typically the walls do not require meshing, as we are interested in the forces at the top and bottom of this wall, where they are significant in this building systems. So that is a general recommendation. But if you want to mesh the walls, there are two ways. One is show you the right-click option to check what are the assignments. For the wall meshing, you can see it is none by default. Right. I select a wall and then go to the shell, and we have the wall auto mesh option. And here you can specify how you want to mesh this. By default, no meshing for straight walls, and auto rectangular meshing for curved walls. You can mesh into specified number of segments, m by n segments, or you can switch to auto rectangular mesh, which specify from the global setting as what is the maximum mesh size you want to use. So I'm leaving to the default. But when you use the wall stack, program has assigned Pier labels automatically. You can see P3, which you can bring in via the view or the set display options, others, labels. Right. And you can see the same Pier label has been assigned for each wall stack. For comparison, I'm going to relabel this Pier label on one of the walls to individual legs. For that, I'm going to assign shell Pier label. I will use modify show definition to create new labels. This is part of P3. Can label it in any way like P4, P5, but just for identifying it easily, and I'm going to label that P3A for this one and P3B for the bottom flange. Now for this, I'm going to apply P3A and P3B. Now these are three different labels, and each leg of this C section will be treated as individual planar walls for the design. And for the left wall stack, this P2, the entire cross section, the C shape, will be utilized for the flexure design. And as far as the shear design is concerned, each leg is designed separately. All right. Now let me add a wall for the face of this opening, assuming that this is a lift core, and then we have walls here with openings. How to model that? For that, let me create a grid. Parallel to I. I'll switch to elevation 5. We can relabel them later. Let me draw the wall and switch to the elevation again. Let me go to the draw wall plan using the same property. Right. Switching back to elevation 5, you have a solid wall. Now here we have the option to draw in elevation the openings in the wall. Draw wall openings, and zoom in. It will snap to the wall panel in each story as you move the mouse on them. There you can quickly click and then start with the help of the small dimensions and draw this opening. Click, and then the opening size also gives you this, and you can create the opening like this, right? And then later you can modify this with the help of the joints in the corners and align them with the coordinates as needed, or move them to specified by specified distance to achieve the dimension of the opening. So that is one way to do it. The other way is specifying the opening size, utilizing it to draw these openings quickly. Let's say width is 1 meter, height is 2 meters, bottom distance is 0 because it is kind of door opening, and left distance, it is 2 meter long. I'm going to provide 500 from the left. Then if I click, oh sorry, I have to lock these before clicking, and you can see these openings are quickly created. Now the next important thing is the meshing for these. We'll have to do this meshing by selecting all the wall panels and the openings together. And we have dedicated meshing under the edit shells, divide walls for openings. So this joint where the meshing, right, of this opening, sorry, the element above this opening and the vertical wall is to be established. That is what this meshing is doing for us. So this is to be done for every opening, whether it is a window opening or a door opening. And then the labeling can go to shell Pier label. For the P2, we'll create P2A, P2B. Now for the elements that are having same X and Y coordinates along the Z can be labeled with the same pair label. So a pair label is associated with the story. So even you can assign different labels, but in practical sense, keeping them for the entire vertical wall stack same is what expected. So that is what program is also giving you the option to label them with the same label. So P2A, and this is P2B. This separation is needed because program allows you to apply labels for wall elements that are spatially separated. So care should be taken on that. So when you're applying these labels, ensure that they are not. Now let's select the spandrel and We'll go with the spandrel labeling again, and the shells, we have spandrel labels separately. S1, here also again the same logic. So the S1 is associated with story 1 and S2 associated with story 2. It's a different spandrel label, but for convenience, you can do this. It's totally fine. Right. So this is about the modeling. Before we come to the design, let us discuss few more things through the slides. Now we have analysis versus design section. So analysis section is what we have modeled. The assemblage of wall or even column objects can be included and assigned with the Pier label, line elements, right? They can also be part of this Pier labeling, and that will make the analysis section. Okay? And the design section is used for the resistance checks. It can use it for design to get the required reinforcement in the flexure, or you can check the capacity. Right? Both are possible, similar to column design. Feature walls can also perform these two. And the important thing is it can differ from the analysis section. Okay. The program allows you to use a different section through a section designer and assign it to the analysis section for the design purposes. So that is allowed. We will discuss this more on this later. And for the flexure design, we have uniform reinforcing, gentle reinforcing, and simplified TNC, which you would have seen whenever you assign the peer reinforcement. So the uniform reinforcing is the default option the program picks up whenever you model this wall from the analysis section. The same section is used in the design automatically, and rebar inside the section is arranged with some minimum bars and default spacing, which you can modify later and apply it. And then general reinforcing is to take you to the section designer and modify the section and the rebar layout, which is typically used and recommended when your geometry is really complex, and then check the design instead of getting the design requirement, check the capacity, and then finally perform the design. That would be our recommendation for walls of non-rectangular shapes in general. So simplified TNC is also available, which will be a planar section defined by length and thickness. It is going to design only the edge members. So intermediate portion of length of the wall is ignored in the strength calculation. Only the ends are designed. So in this type, we can perform only the design, no checking is possible. So Pier and Spandrel labels we have seen, and the definitions we have seen. But important thing here is these design stations available. So piers will have two, bottom and the top of the wall will be designed, right? So in case you want a design output at the midsection, then you'll have to break the wall at the mid height and then label them separately, right? So that is how you'll go about it. And spandrels, it is going to provide output only at two locations again, on the left and the right, the coupling beams. So in case you want the variation of the forces to be captured along the length of the spandrel, then you'll have to mesh the wall elements modeled for the spandrel and then label them differently to capture this variation. The catch here is the diagonal reinforcement, if required, will be calculated for each segment, which will not be correct. So in that case, when you're breaking it for other reasons that force variation is necessary, then you'll have to manually calculate the diagonal reinforcement. Right. So the scheme of pair labeling, you can see you can label them. If it is meshed, then P2. And if you want a different section output for this left side on this opening, then you are labeling it. Naturally, you're labeling it a different name. So all the elements that are connected together can be labeled as P1. That is also okay. So here you can also see parallelly the spandrel labels have been done as we did. And this spandrel element can contain both a Pier label as well as a spandrel label or any one. So depending on the design needs, the forces you're expecting, you can decide on this labeling. So a detailed procedure is explained in our design manual, but I'll try to cover them briefly here. Let us move to the design of piers. So the P delta effects, we recommend that you perform the P delta analysis always. So the global sway effect are captured in the primary analysis itself, and then the local effects shall be captured using the code specified additional moment that arises due to slenderness rather than meshing the element itself. But if you mesh the elements, these local moments are also captured in the P delta effects, right? So the program conservatively takes the effect length factor as 1. When shear walls are there, then most likely the poems are going to be praised on this assumption. And anyway, we are recommending the P delta analysis, so those sway effects are already captured. So conservatively, the effect length factor K is set to 1 for the design purposes. So the types simplified C and T is a planar design. So minor axis I mean, in other words, the major direction forces are used in this compression and tension design. The web is ignored, and the section designer based, which is both the general and uniform. In general, you'll be taken into the section designer where you will have to provide the cross-sectional information, including the rebars, and the uniform is simplified one where it can take only the uniform rebars for quick numbers. But we would like to emphasize that the shear wall design is iterative in nature, unlike the column design. So you'll have to do some iterations in terms of checking the capacities and then finalize the design. And one other important thing is modeling of columns as walls. We do not recommend modeling columns as walls because um, you, the wall elements, the design of the wall elements will be slightly different from the column. The design checks required for column design will not be available for the walls. So these are the two reasons. And the ratio when to decide whether it is a wall or a column is already the code. You can follow that. But you should be aware of the design checks that will go with the column and the wall. Within the C and T method, So we have three conditions that can be satisfied. You can leave it completely to the program. Program will increment the uh, edge member length automatically till it is satisfied. Or you can also specify user-defined edge members and design for it, and it will reply in the design output whether it is safe or not. You can also consider one edge is specified and the other edge is variable. Then program can do all the three conditions. And in case of general and uniform reinforcing, a PMM interaction surface is generated similar to column, and it uses the utilization factor as a limit, but you can set it to 1 or 0.95. So basically, for each design combination, it performs a design and it checks this ratio, OL to OC, that should be within the utilization factor limit. If any one ratio from all the combinations exceeds, then it's declared that it is failing. All of these combinations are within this capacity, then the section is safe. And for the design, program uses 8 reinforcing ratios, specified IP min and IP max values in the design preferences. You can see, and the table here displays the ratios and how the ratios are calculated within. So 8 ratios with 0.0025 and 0.02. So our recommendation is to start with this ratio. The default ratio in the preference will be 0.0025 and 0.04, which will be a wider range. So keeping it smaller and iterating the design a couple of times till the required ratio is bracketed within these limits. So that's how you should go about this when you're designing the piers. So the design check also includes the minimum eccentricity, the slenderness, and it generates interaction surface, and boundary elements requirements are reported for the seismic case. When seismic forces are involved, this check is performed, and it does not design the boundary elements in that case. The reason is that you have these boundary elements arbitrarily designed, so the design will have to take care of that. For design, you can also utilize the CNT method that is already available within the program. Right. So I have an example, the wall additional moment calculation. And this is for a wall that is a double-story height. I have an example. I'll open that in the ETABS to understand this quickly better. So story 2 has no slab or beam connection to these walls. You see this. So basically, it is a double-story height wall. The design is performed. This is to demonstrate you the for this wall. You right click. Yeah, this is to demonstrate that the program automatically calculates the unsupported length from the connectivity of the beams, slabs, and diaphragms in different levels. In this case, That unsupported length will be 2, and you can see. So on the left is the output from that lower wall, but it is double story. It is the mu2, which is the minor direction moment, 86.9, and it is computed involving the initial moments and the additional moment requirement. So importantly, you should note the K value used for this calculation from the axial and analysis moments from bottom and top for that wall. So for a particular combination, D wall S14, and you can see this additional 80 is calculated and initial, and both are added to arrive this. This is to demonstrate that program automatically calculates the unsupported length. Right. Yeah. And on the pier design for the single pier label and the multi-legged, you can see the design output, how it is reported. Right. When it is single, you can see the for the C section, a single output for each story, top and bottom. When you right click, right. The program identifies the legs, but for the flexure, the entire section or the shape is used for the PMM interaction and is giving you a single output for the top and bottom, how much rebar is required, right? And in the shear under boundary element checks, it is going to report it for individual legs. And for individual leg pier labeling, you will get so if you notice this is for individual legs, so only one leg in each, and the shear and boundary element checks are only for leg one, only cross section here. So the important thing to note is when you are using this single pair label for all the legs of this cross section, then it is going to be a single output. But here, the individual legs will have the flexural reinforcement, the vertical reinforcement specifically. You can see here this leg is 2310, but the other leg is 1593, right? You can imagine this in a real structure where you will have this requirement in some of the legs where the axial force is significantly high in one of the legs. So that information will be lost in the single labeling or the same pair labeling section. So we recommend that you do this And if the distribution is fine, the axial loads are well distributed across the section, then you can use a single pier label. But we recommend you use both in your design iterations. We should not miss this information and allow that particular leg fail in a real situation. Right. Now, walls for the shear. So only the major direction, the in-plane shear force are designed. The required reinforcements are calculated, and the capacity of the concrete or the concrete strength will be based on for non-seismic as per IS 456. H by L ratio will be used, and when seismic loads are involved, then tau CD is calculated as per 139201456, table 19, and in tension VC is set to 0. So tau V minus tau C, that for the difference, you'll calculate the shear reinforcement as usual. The procedure is explained in detail, but I just want to highlight the key points here. And spandrel design, the flexural design, it can design for uh, both rectangular and T section. So again, you have the analysis section versus design section here. So the program allows you to specify the dimension of the design section directly when you right click of a spandrel. The overrides, you can do this. So for the negative moments, always designed as rectangular section. Positive moment, uh, designed as a rectangular section or a T section if slab dimensions are specified. Right. So this information is available through the overrides for you. And the design criteria it uses a simplified parabolic concrete stress block as usual, but it also checks for the deep beam. So L by D ratio less than or equal to 2.5. The lever arm limits are imposed and the design is performed accordingly. So both are. And for the shear design, the regular vertical stirrups are designed as usual, is provided here. And the ratios are reported at ASV by SV ratio, similar to beams. And importantly, the diagonal reinforcement, which are involved when a seismic load is present. And it is required if the aspect ratio is less than 3 or the code specified tau v value is greater than the given expression. So the reported area is the area for each diagonal. So you have two diagonal X. So each one need to satisfy this required area reported in the structural design. Let us quickly go through the design preferences, settings that are available. And one more discussion on the general reinforcing with the ST sec. So here we are setting the code and then the rebar material to be used and the factors. So the Pmax factor is for the simplified CNT method. So number of curves and points, this is for defining the interaction surface. So consider minimum eccentricity, yes or no, control is given to you. And edge design for the CNT method again, how much is the max ratio. And the section design, IP min and IP max for the uniform and the general reinforcing sections, the ratios, which I was talking about, the ratio 0.0025 and 0.04. You can reduce this, ensure that it is bracketed within, because the interpolations will happen in calculating the required rebar when the range is large, right? So it might give you slightly higher reinforcement. So if you bracket it, let's say 0.5 to 2%, or let's say 2 to 4%, if the requirement so, then the required calculated reported required rebar will be much closer to the actual. So that is an important input you should take. And the utilization factor limit for the interaction surfaces, the default is 0.95. You can set it to 1 or 0.9 to be more conservative. All right. Now, how will you access all of this? So when you have a wall, let's go to the elevation C. Let's focus on this planar wall. Design, shear wall design. To define general pier section. This is the one you use to enter into this section designer to define the section. We'll come to this shortly. For that, we'll select the walls before performing the design. Right, we can select all of them. And if you go to design, shear wall design, we have assign pier section. So even before you start the design, if you don't specify this, program by default picks up the uniform reinforcing. But if you want to specify this, and if you pick this simplified C and T, then no inputs required. It will simply perform the design for simplified C and T. Let me do this. I assign this, and then if I perform, and it will give the rebar on the left end and the right end. Right, you right click. So basically, it gives the top and bottom and left and right edge length and how much rebar is. It's designed as a short column, and you'll get the design output. Now, if I change this to assign pier section, uniform reinforcing, you can specify even the material and bar size. 12, 200, pier cover is 25, and the corner bars that is also 12. And here you can specify reinforcements to be checked or designed. Let us go with the checked. Perform the design again. Now it will show the total rebar specified for the section through the uniform input. So 2488. If I go to the design output to the info, and you can ask, by default it is showing the longitudinal reinforcing. That's why it is showing the specified longitudinal bar. But we are interested in the ratios, Pier DC ratio, demand capacity ratio, and you'll be able to see this. You right click for the bottommost, and then if you look at the flexural design, you'll see the demand capacity ratios pretty close to 1. So the provided reinforcements are fine. You can proceed with this reinforcement. But maybe in higher levels or the higher stories. You may not need this much, but you can decide on that with a different reinforcing ratio. So because in practical sense, you will not be providing reinforcement, um, changing it every story level, but you might be looking at those critical levels or the stories where the significant changes, and then you'll be grouping, and then the reinforcements can be specified. So you should think this input in that aspect. And the last one is general reinforcing. So define general peer sections. You can create by pressing add peer section, and you can create a new section completely from add new peer section, or you can pick from the existing one. I'll use P3 as the input from story 1. It's a C section. So this is P3 so we are looking at. And here you got the section. Here you'll have to give a name, some name, and then material and reinforcing. You can specify directly from here. Should be much easier. Tie bar, size, rebar material. Press OK. Then it will generate reinforcement inside the section. Additionally, you can provide more reinforcement using the rebar shapes as single rebar. So single rebar can provide more rebar like this from here. So first you click at the required location approximately, and then you can fine tune this. So I'm actually trying to enhance the section capacity by providing more reinforcement on the wall ends. Now for this uniform reinforcement here, you can modify these values, say 25, bar size 12, apply to all edges, right? Then the corners, you can apply to all corners. Now you are left with these individual bars, which you can right click and work with their exact coordinates to position it properly, or you can also utilize replicate commands to create in a row, or you can use rebar shape in a line or in a rectangle, right? So a bit of an effort is needed to do this input. Let us assume this is okay, and I'm going to accept this. And we have a section called Pier 1, the list. Now to these, so to these walls, now we can assign this pier section we just defined using the general reinforcing pier 1, pier 1 for both top and bottom, and can leave it to reinforcement to be checked. Okay, and perform the design one more time. Now it is reporting the demand capacity ratio. Now when you right click, you can see the capacity. I have provided slightly more reinforcement than the default one, the uniform one. And you can see the demand capacity ratio is significantly lower with that input. And you can quickly check the PMM interaction surfaces. is to ensure, right, if the refinement is okay or not. So you have the option to modify the number of curves and points, specifically number of curves, to make the refinement as needed. So the default is 24. You can raise it to 48, 72, something like that, depending on the refinement level you need for the interaction surface. All right. Yeah, I think I've covered most of the topics I wanted to be discussed in this webinar. If you have any questions, then please let me know through the Q&A. I will try to answer this. Yeah. Stiffness modifiers I had discussed in one of the previous uh, webinar session. Um, Stiffness modifiers for the walls, you can apply it to the F22 modifier, which is the vertical, and you can also apply it to F11. So F11 and F22 or F22 alone, you can give the modifier specified in the code. That should do. So there is a question on where to end the beam, on the face of the wall end or inside the joint, the shear wall. So this is in the major direction, right? We recommend modeling till the end of the wall. If the walls are not meshed, which is a typical uh, use case, when if walls are meshed manually, then till this second joint in that direction, you can take it there. But the implication here will be in the design uh, where the plastic shear calculation will use this length, right? There you should be very careful how we are doing it. Uh, so based on that, you can decide. Or what you can also do is you can break this beam at the wall end, and if you're extending it, the next piece will be a separate element. Please check that and let us know if you have any further questions through our. Yeah, I think the additional moment thing, that's the more moment that you notice in the minor direction, which I already explained. But if any discussion on a specific model, then please contact us on that. We'll clarify the results. So what is the mesh size that can be followed? Yeah, typically walls can have a size of 1 to 2 meters of mesh size. The single pair label and the multiple leg having different names. Um, so the benefit is you're going to get the entire cross section for the flexure design, right? If the assumption is so, then you can use that, but you might miss the um, heavily loaded leg in that case. So you have to check both. Okay. If the beams are connecting at different, not in consecutive floor levels, about the double story height or triple story height, right? There are no overrides directly. You can specify this unsupported length, but it has to be established through the connectivity in your model. Yeah, if the wall is in tension, yes, program can design the wall for tension. So you can check the design output. So the wall and sorry, the pier and spandrel label for different purposes, like uh, the coupling beam is the main element for which you're going to assign the spandrel label. But if the wall is continuous above the opening, then you can go with the pier label because the forces in the axial direction is significant. So you have to decide on that, or you can assign both and check the output. And you have to do the detailing accordingly for that situation. I think I have answered most of the questions. Some of them are repetitive, so I hope the presentation was helpful to you, given it is the basic understanding of the features and the usage and our recommendations. But there might be specific queries, obviously, and that shall be discussed uh, directly through our support. So please feel free to write any queries, support@csispl.in. So thank you all for joining and your time. We'll meet you soon in another session. Bye for now.